Customer said you can get a hat on this.
Yeah.
I thought it was, but I wasn't certain.
Okay, we'll go ahead and get started. Can everyone on Zoom hear me and see the slides?
Yes.
Yes.
Thank you. So I'm still taking roll, but so there's one person that I'm not certain if they're on Zoom. Addie Cascanet, are you there? Okay. I think that's the only person I don't have accounted for, so, all right. So Tuesday, when we had class, we talked about intermolecular forces and went through a lot of that stuff and really focused on how those intermolecular forces impact some of the physical properties that compounds can have. And a lot of it we talked about centered around boiling point. But we had also mentioned that in addition to boiling point, it impacts melting point, viscosity, surface tension, capillary action. And so what we're going to do today is we're going to talk about some of these others. And so viscosity, surface tension, capillary action, those may be new terms for you. So we'll kind of talk about what it means. We'll talk about how the intermolecular properties, those interactions, impact those physical properties and kind of why it's important. And then we'll go on and do some things about phase changes and stuff like that and some calculations and some energy / heat type calculations with that. So that's the plan for today. We should get finished with chapter 11 today. And remember, next Thursday, we'll have a quiz and it'll cover chapter 11. And then next week on Tuesday, we'll start up with chapter 12. So viscosity. Viscosity is defined as the resistance of a liquid to flow. And so basically, the way that what that means is kind of how thick something is. And so if you're pouring it and it takes a while for it to come out or move slowly, then it's a viscous liquid. And one area where you see viscosity numbers reported a lot is in motor oil. And in the picture on the slide, we have an SAE 40 and an SAE 10, two different motor oils. That SAE number is an indicator of the viscosity of the oil. So the lower that number, the lower the viscosity, so the less thick it is, and so the easier it is to pour. So if you ever see, like in your car manual, you need a certain SAE number for the oil, that's telling you how viscous the oil needs to be to work in that car. The other example I always like is syrup. Syrup's pretty thick, pours usually pretty slowly. That's a fairly viscous liquid. Honey's another one that's real viscous liquid. You can pour them, but it's pretty slow. The reason why they're viscous is the compounds have a lot of interaction with each other. So viscosity increases, the stronger those intermolecular forces are. The other thing is, as you increase the temperature of something, you can reduce the viscosity of it. And that's because you're putting energy into it, and then that energy going in maybe disrupts some of those interactions that you would have. And so, and you think about it just from a practical perspective. If you have, for instance, some syrup or honey or something, and it's really, really viscous, you can heat it up and then it'll pour a little easier. So that's the kind of thing that I think we all intuitively know, but viscosity is the term that we use to describe that thickness, that ability to pour something. And like I said, in the motor oil example, the higher that SAE number, the more viscous the oil is. Here we have a table with a series of hydrocarbons, a series of alkanes. And we see we start with hexane, go down to heptane, octane, nonane, decane. So it's C6 through C10 alkanes. And what we see is, we see the viscosity getting larger, right? So 10 to the minus 3 for decane is higher than the 10 to the minus 4 value for hexane. Any thoughts on why that viscosity is getting higher as we go to those different molecules from the C6 to the C10 chain? Yes.
It's more compact.
It's more compact. Okay, what do you mean by more compact?
It's harder for the molecules to move around.
Okay, any other thoughts?
A thicker structure.
A thicker structure. What do you mean by thicker structure?
Like the more the different like breakdowns, the more that there are, the like thicker the compound itself would be.
Okay. Any other thoughts? So on Tuesday, when we talked about, because the structures of these are all pretty similar, right? We're just adding one carbon with each one down. They're all a nice straight chain thing. So the geometry is going to be pretty similar and all that. Do you remember one of the things we talked about with the intermolecular? Well, first of all, let me ask you this question. Can these hydrogen bond? Got a lot of hydrogen there. Can we hydrogen bond? I see heads shaking no. Why can't we? Why do you think we can?
There's no NOF.
Right. We said for hydrogen bonding, because remember when we talked about those intermolecular forces, we said hydrogen bonding was like really a good one. And when we talked about kind of rating them, that was the highest rated one. Well, but we have hydrogen, we got plenty of that. But we don't have that electronegative atom that it's bonded to. We said it needed to be bonded to oxygen, nitrogen, or fluorine. And then that hydrogen could get a little electron deficient, and then it could do some hydrogen bonding with something else. So we can't do that. So we can't do hydrogen bonding. Are these polar or non-polar? Any thoughts on that? Remember, we said to be polar, we needed what? What did the element need to be? What did the atom need to be? We needed something that was electronegative. These really are electronegative. Carbon's not really electronegative. So it's not polar, so we don't have the dipole-dipole thing going on. We don't have the hydrogen bonding going on. So then we just kind of have those lower level dispersion forces. What did we say about those lower level dispersion forces? We said that the more electrons you have in the molecule, the stronger it's going to be. But we also said that the higher the molecular weight or the bigger the molecule, you're going to have more. And that's why you're getting more viscosity for this one, the bigger one, the decane, than you do the others, so like hexane, for instance. It's a bigger molecule, there's more of that. So the answers I got were sort of right, but really it's just a little more simple than what you guys are thinking, I think. It's just mostly there's more stuff. So if you have a little bit of interaction at a lot of spots, that kind of builds up and makes it a little stronger. And so that's why we see this gradual increase as we kind of go up, adding that extra carbon to each of the molecules as we go up. So in this case, this is a good comparator because these molecules are, as I said, really similar. They're all alkanes, they're all straight chain, so we don't have any other confounding factors in evaluating it. It's just they're just getting a little bigger, and we see that viscosity increase as we do that. And we know that viscosity, as it is related to those intermolecular interactions. So the more of those we have, we're going to increase the viscosity. Okay. Let's talk about another one of the terms, surface tension. So surface tension, the definition of it is it's the energy required to increase the surface area of a liquid by a unit amount. So that's kind of a what the heck does that mean type of definition, at least to me it is. So let's talk about what that means from a more practical perspective when we talk about surface tension. Surface tension, if we look at the cartoon on the slide here, we see a bunch of molecules here, and we see them interacting with each other, kind of in the middle of the solution. And what we see is we see it kind of interacting above, beyond, below, to the sides, all around it. When we get to the surface, though, what we see is we have interactions to the side and below, but because there's no molecules above it, that's the air, there's nothing pulling it upwards. So the one in the middle, as you can see from the little arrows, is kind of being pulled in all directions. It's kind of, the one up here is just being pulled down and kind of to the side. So it's not going up. It's this kind of interaction here of the molecules pulling it in versus the air interface. That's really what we're describing when we talk about surface tension. And so some of the results of this, one that you see all the time is water beating up. So if the attractions of the water within itself are stronger than the attractions of the water to that surface, then you get the beating up. And that's related to surface tension. The other one is people will say water can kind of act like it sort of has like a skin or whatever. Did you ever see like these little bugs if you're at a lake or something kind of skirting across the water? Well, that's because of the surface tension thing, is that surface tension of the water keeps it so that the bug isn't heavy enough. Even though it's more dense than water, it's not heavy enough that it can kind of skirt over the water. So surface tension is typically measured. There's something called a Denoy tensiometer, which is often used to it. And really all it is this little platinum ring that you dip down into the water, and then you start pulling it up. And what you'll see is you'll see the water kind of hang onto the ring and pull up, and then at some point it'll let go. And it's measured in dynes, D-Y-N-E-S, and that measurement is how they get what surface tensions are for liquids. Like I said, the dyne measurement is really more just to give you relative surface tension strengths of liquids. But for us, when we think of surface tension, the bug kind of skirting across, the beating of water, those are examples of surface tension kind of at work. Okay, two things that are a little bit related to surface tension, kind of similar, are cohesion and adhesion. So if the intermolecular forces keep the molecules kind of bonding, interacting, not bonding, but interacting with each other, that's called cohesion. Cohesive. And you think about it, just in your normal conversation, if you say something's cohesive, you're saying it's kind of together, it's stuck together, staying together. If the intermolecular forces are such that they have the substance interact more strongly with the surface, then that's called adhesion. And so you think of it adherence and things, terms like that. So cohesive forces, ones that result in the molecules kind of staying together. Adhesive is they're interacting more with the substances around it. So the surface it's sitting on or the container it's in, something like that. Cohesive and adhesive forces come into play in something called capillary action. So does anyone have a guess at what capillary action is? First of all, what is a capillary? So in this definition, capillary is usually a small glass tube, is typically. There's like medical capillaries, but in this case, it's a small glass tube. And if you think of like a thermometer, that liquid in there would be kind of in a capillary. So you're using capillary action to have that go up or down. The rise up these narrow tubes, that's what's called capillary action. And so you have a couple things going on here. You have the adhesive forces and you have the cohesive forces. think about when we were in lab last semester and you were reading, say, for instance, the burette. We had to read that meniscus, right? And the meniscus was that little dip of the solution at the top, and you'd read the bottom, okay? So did you ever think of why it dipped down instead of just straight across? The reason for that is this cohesive and adhesive forces. So in the picture we have here, on the left, we have some water in the tube, and on the right, we have mercury in the tube. And it's a little difficult to see on the slide, but if you look closely, you can see the water is kind of higher on the edges that are in contact with the glass, and then it kind of dips down. So that's a concave type of meniscus in this case. If you look at mercury closely, you'll see it's just the opposite, is that it actually goes down a little bit on the sides and kind of goes up in the middle. So that's a convex type of meniscus. And so why is that? Well, what this is telling us is that with water, we have our cohesive forces. So that's within the liquid, the molecules attracting to each other. And then we have the adhesive forces, which are the water molecules interacting with the tube walls, okay, in this case, the glass tube walls. This is telling us that we're actually getting more interaction with the walls than we are with the molecules internally. And so that's why on the side it goes up a little bit more, okay? And that's why you get that kind of dip down with water. Mercury is just the opposite. Its cohesive forces, so in other words, the intermolecular forces within it, with each other, are stronger than its interaction forces with the sides of the glass wall. And so because of that, it's staying together and the sides kind of dip down on that. You don't have that change there. The other thing, the reason why the water does that is that glass is made of silica, and silica has SiOH groups. And the hydroxide on that silicon tends to deprotonate and have a negative charge. So it's Si bonded to O negative. If you remember when we talked about water, we said what? It's a very polar molecule. We have that oxygen. We have the two hydrogens. We have like partial negative charge on the oxygen, partial positive on those hydrogens. So those hydrogens on the water really like to interact with that negatively charged SiO group on the glass. So that's what's going on from a chemistry perspective with that meniscus and the water and all that. So here's an example of having those adhesion and cohesive type of forces impacting, in this case, just how the water and the mercury flows through that capillary action to rise and fall. Any questions about the differences between these two? Okay. So now we're going to go and we're going to talk about phase changes, and we're going to talk about some energy calculations associated with that, and how that material goes from one phase to the other, kind of the process in a step-by-step fashion. And so what we have here is a chart which kind of shows the different phase changes we're concerned about. And when we say phase change, we're talking about the matter going from solid to liquid, or liquid to gas, or gas to liquid, gas to solid, those kind of physical changes from one form to another. When we have a change, either energy goes into it or energy comes out of it. If energy is put in, is that endothermic or exothermic? Any thoughts on that? Endo, right. Easy way to remember, endo, in, endo, in. Exothermic is heat going out. So on this diagram that we have, The ones in blue are endothermic processes. So in other words, energy has to be put into the substance. And the ones in red are exothermic processes, which mean energy is released, is coming out of the substance. So let's just kind of go through this a little bit. So here we're seeing that we start as a solid, we go to a liquid. So that would be melting. And so there we see that's an endothermic process. Kind of makes sense, right? If you had a ice cube, for instance, and you wanted to melt it, what would you do? You'd heat it up, let it sit out, get it warmed up, add some heat to it. So that's that endothermic process. If then we have a liquid and want to change it to a gas, vaporization, once again, you would add energy into it, add heat into it, to have that phase change from liquid to gas. And then the other endothermic one is if you have a solid and go directly to the gas, which some materials you're able to do that with, that's called sublimation. So if you've ever had dry ice, anyone ever have dry ice and you drop it on the floor, or liquid nitrogen or things like that, you never have to clean that stuff up, right? Because dry ice goes from solid to gas. And so once again, you have to put energy into that to make that occur. Coming back the other way, we have some that are exothermic. So if we go from a gas down to a liquid, so it's a condensation type of situation, then that's going to be exothermic. Heat's going to be given off. Same if we go from liquid to freezing. So we have something liquid, we want to freeze it, we need to be pulling energy out. It's an exothermic process. And then finally, if we go from gas to solid, that deposition is also exothermic. So when we're talking about phase changes, no matter which of these it is, we can think of it in terms of exothermic or endothermic processes in kind of like stepwise fashion that we go about. So there's a few terms that we need to be familiar with in order to do some of these calculations. And so as we're talking about energy changes and we're talking about change of states, one term that we use is the heat of fusion. And heat of fusion is the energy required to change a solid at its melting point to a liquid. So heat of fusion means you've gotten to the right temperature, okay, whatever that melting point temperature is. So you've gotten the solid to that, and now you want to convert the solid to a liquid. That value is the heat of fusion for that material. Another term is heat of vaporization. And similar to the heat of fusion, this is the energy required to change a liquid at its boiling point to a gas. So once again, you've raised the temperature to where it needs to be, and now you're doing that conversion from a liquid to a gas. And that's known as the heat of vaporization. And then the third one is the heat of sublimation. That's the energy needed to change a solid directly to a gas. So once again, you get it to the right temperature, and then the energy that's needed to make that physical conversion is the heat of sublimation. So the key here is that these are the energy changes associated with that change of state, whether it be solid to liquid, liquid to gas, or solid to gas. That would determine which of these values you would be given, okay? Any questions about these definitions? So these come into play when we start to figure out the energy that's required to make some transition from one temperature to another or one state to another. And a visual way of seeing what's going on is what we have here. And this is a graph of temperature, so temperature on the y-axis, and heat added on the x-axis. And these are called heating curves. So these are really good to give yourself kind of like a visual picture of what's going on and what steps are involved in that transition. So I'm not saying you got to draw these out every time you do one of these calculations, but you should at least be kind of thinking in terms of this. And if it does help you to kind of draw it out, go ahead and draw it out. So let's kind of walk through this heating curve and what we're saying is going on. So this one is for water. And so it's saying that at point A, we're starting at minus 25 degrees C. So I think we all know the freezing point of water is 0 degrees C. So at minus 25, we have solid water, ice. We go ahead and we can see we're adding heat. So the A to B is the adding of heat. And so B is a little bit down here. So it wasn't a ton of heat that was added, but it was added and we see the temperature goes up to get to that point B. That point B is at 0 degrees C. So now the next step is we've changed the temperature. Now we have to add heat to get it all to melt. And what you see is that as you add more heat, so heat's being added, that's this little B to C red line, that the temperature is not changing. So all that energy that's being put in, all that heat that's being put in is causing the phase change. So it's going from solid to liquid, but the temperature is not changing. We need extra energy in order to then get the temperature. At this C point, that's telling us everything is melted. And so now as we put more heat in, we're seeing the temperature go up, okay? Then we put more energy in, there's no more of this process of melting, and so now the temperature starts to go up until it hits point D, which is 100 degrees C, and at point D is where now we're at the boiling point, okay? So now the liquid, we're trying to convert all this liquid into vapor. And what you see is, as you go, you add heat, add heat, add heat, add heat, add heat, add heat. Eventually, at point E, we've added all the heat to convert everything into that vapor phase. And then as we add more energy, then we start to see the temperature go up again. Okay, and then that E to F, then that's all vapor phase there. So what it tells us is we have, in this case, if we were to go from this minus 25 up to positive 125, we'd have multiple steps. We'd have to calculate the energy that's involved. We have this minus 25 to 0, the energy calculation there. Then we have an energy calculation going from B to C. We have another one going from C to D, a calculation for D to E, and then E to F. And then we would add up all of those values to find the total energy that was required to go from point A, ice, at minus 25, up to gas phase water at 125, positive 125. Okay? So this is what we're worried about, or what we're going to be doing from just a conceptual thing. You'll see there's some problems we'll do and some homework we'll do where we actually put numbers in and do some of these calculations. So don't forget about this. Don't forget conceptually how things kind of move along when you're going to put the numbers in. In other words, don't let the numbers confuse you, okay? Okay, so any questions on anything we've covered so far? All right, I'd like to take a look at a little bit of homework here. So these are homework problems I would ask you to take a look at. I'm going to pull a few of them out and we'll go over them now. The other thing I want to remind everyone just is that as you work on the homework, if you get stuck on something, all the homework answers are posted on Canvas. So you can look it up. If you're still confused, send me an email or something and I can try and help you. Okay, the first one, 1135. So 1135 says liquids can interact with flat surfaces just as they can with capillary tubes. The cohesive forces between the liquid can be stronger or weaker than the adhesive forces between liquid and surface. In which of these diagrams do the adhesive forces between surface and liquid exceed the cohesive forces within the liquid? So we have these two figures. We have one, the top one that looks like a little ball sitting on the surface, and the other one is a little flat, more flattened out. So which of those do you think is an example of adhesive forces being greater? So remember, adhesive force, once again, is the interaction of the material with the surface. Yes?
Is it the circle one?
So, okay, so the circle one is, we just got a little bit interacting with that. This one, we've got a lot interacting. So if I'm thinking adhesive forces, then I'm thinking that the surface is more attracted to the molecules.
Okay, that's what it's
Okay, and remember, cohesive is the molecules themselves are really together. So in this instance, the one on top would be more cohesive. They kind of stay together a little bit better. So it winds up being a little like a drop or a ball or whatever you want to think of it. This second one, where it's a little more flattened out, that tells me that interaction with that surface is a little bit stronger than the interaction between the molecules themselves, okay? So let me ask you this. Does anyone remember if water is polar or non-polar? Yeah, it's polar? Polar, right. 'Cause remember we talked about water likes to form a dipole and all that kind of fun stuff. So if something's forming dipoles, it's polar. If it has a little more electronegativity, it's polar. So water is a very polar material. If we put a drop of water and it looked like this top one here, the circle, the nice circle one, not the mush down one. If we put water on the surface and it looked like that, would we say that surface is more likely polar or non-polar? Any thoughts on that? Before you answer, I'll give you one other clue. There's kind of two things we've talked about. One is opposites attract, right? And that tends to be with charge, we're talking. And the other is like dissolves like. So polar stuff dissolves polar stuff, non-polar dissolves non-polar stuff. This isn't dissolving anything, but it is an interaction. So if the water is polar and it's beating up like that, do you think the surface is polar or non-polar? Yeah,
Non-polar.
non-polar. Why do you say that?
Because if it was polar, it would stick together.
Yeah, it would mush down like this. So in these two examples we have here, the top one, that surface is more likely, assume this is water in the drought. That surface is non-polar. This one is more likely polar because it's kind of mushing in with it. It's interacting more with it. So I think it's supposed to rain today. And so I'm looking at what each of you is wearing in the class. And do you think what you're wearing is going to be good for the rain? No. So do you think what you're wearing is polar or non-polar? Polar, yeah. So if you had a raincoat on, and you think of what happens with the raincoat, right? The water gets on it, it usually beads up, rolls right off. That raincoat has something in the material that is non-polar. And that's the whole idea behind that.
I have a question. So
Mhm.
you said the water droplet is polar,
Yes,
but opposites attract, correct?
opposites attract, and when we talk about opposites attracting, we're talking about charge.
Okay.
So plus and minus go together, plus and plus repel each other. So opposites attract when we're talking about cations and anions and charge, like, so pluses and minuses. When we're talking about polar and non-polar, then like dissolves like. So in that case, if it's two polar things, they'll go together. The one way to think of that also is, if you ever think of vinegar, if you ever see like salad dressing that separates in the bottle, you can shake it all you want and it kind of mixes, but as soon as you let it sit, it separates again. That's because one of those phases is very polar and the other phase is non-polar. It's usually a vinegar and oil type, usually a water-based and an oil-based type. Oil tends to be real non-polar. It usually has a long hydrocarbon chain in it of some kind. And that's why those don't mix. You can shake it as long as you want. As soon as you stop shaking, it's going to slowly start to separate. There's a whole field of chemistry where people look for things to make a polar and non-polar thing go together and not separate. Okay, I mean, we're not going to get into that here, but that's a big deal of figuring that stuff out. So, okay. All right, what's the next one here? So the next one, 11.39. So in 11.39, we're going to name the phase transition that indicate whether it's exothermic or endothermic. And remember, endothermic means you got to put energy in, put heat in. Exothermic means it's coming out. So the first one, you have a piece of ice and you change it to water. So in other words, it's a melting process. So what do you have to do to melt ice? Put heat in or pull heat out?
Yeah.
Heat in. So heat in, it's an endothermic process. The next one, you have some wet clothes, you hang them out to dry in the sun. So that's evaporation, right? So you're going from liquid to gas. Endothermic or exothermic, what are you doing? You're putting heat in, you're taking it out. So that's sunlight, right? You're usually doing the trick. So that would be a heat source. So it's endothermic, heat goes in. The next one, frost on a window. So when you wake up in the morning, you got to scrape your car windows. Where'd that come from? Well, it was moisture, water in the air. It deposits there, so it goes from vapor phase to solid. So is that endothermic or exothermic? Yeah.
Excellent.
Exo, yeah, heat's coming out. If it was endothermic, then we'd be scraping our windows all day long, right? Because the heat's got more into it. And then the last one, water droplets on a cold glass. In this case, they're saying lemonade, but a cold glass of some liquid, some drink you have. So there, once again, you have vapor, water, it's in the atmosphere. It condenses on that glass, so it goes from vapor phase to liquid. Exo or endo? That's another one of those exothermic. We didn't have to put any energy into that. We're actually pulling energy out, right? The energy is given off. And you think about it, if one way to think of it is that glass is cold, right? So it's a source, it's sucking up energy. So energy is coming from somewhere, it's coming from that water in the atmosphere, and the result is you see it on the outside of the glass. So, yeah.
Can you give an example of whatever the sublimation is?
Sublimation. So the best one I could give you is dry ice, if you've ever seen dry ice. Have you ever seen dry ice?
Yeah, is that like the only one though?
There's some other compounds, but that's the easiest one I can think of right now.
Okay.
And that's the one most people are familiar with.
Mhm.
So like if you have a piece of dry ice immediately you open the freezer chest, all that vapor comes up. And then if you take a piece and throw it on the floor, within a few minutes, if it's a small enough piece, it'll be gone. That's a good example of sublimation.
Okay,
There's some other things you can do to do sublimation, but like I said, that to me is the one that most people are familiar with. So, yeah, any other questions before we go to the calculations? The fun stuff? Okay. So let's take a look at a couple calculations here. And I'll just tell you right now, these types of calculations will be on the quiz, they'll be on the exam. So you want to get comfortable doing them. And so we'll go over a couple here today. I would encourage you to go and do some of the homework problems so you get comfortable doing them too. And get comfortable with the general idea. For these types of calculations, as I was saying, the kind of thought process of the transitions are what we talked about in this heating curve example, okay? And remember we talked about there's a heat calculation from A to B as we change the temperature. There's heat calculations from B to C as we change the phases. Heat calculation for C to D, once again, as we change the temperature. D to E as we change the physical state, and then finally E to F. So there's multiple heat calculations, and it just, different problems will ask you to calculate different portions of this. But this kind of thought process is what you're going to use. Okay, so in 11.45, let me read that one to you. It tells us that ethanol melts at 114 degrees C and boils at 78 degrees C. Okay, so if we go back to here, this would be the melting that they're giving us at this temperature. And then this would be the boiling temperature. So for water, it's 0 and 100. For ethanol, it's minus 114 and 78. Then it tells us that the enthalpy of fusion of ethanol is 5.02 kilojoules per mole. And the enthalpy of vaporization is 38.56 kilojoules per mole. Then it tells us that the specific heats for solid and liquid ethanol are 0.97 and 2.3 joules per gram Kelvin for those two. Then it wants us to say how much heat is required to convert 42 grams of ethanol at 35 degrees C to vapor phase at 78 degrees C. So once again, going back to this plot, so 35 would be here, is above our freezing point that we had, and then we're going to go up to our boiling point. So the first thing we do is we go ahead and we're going to see what this delta in temperature is, because we know we're going to need that information. And so 35 to 78 degrees, that difference is 43 degrees. The other thing we're going to do is we're going to go ahead and find out what the molecular weight of ethanol is. And that's what we have calculated here. So 2 times 12 for the carbons. We have 1 oxygen. So that's 16. We have 6 hydrogen atoms for 6. And so that total molecular weight for the ethanol is 46. And you say, why in the heck did I do that? Okay. Well, one tip-off was when I look at my constants, okay, remember our friend dimensional analysis that we talked about a lot last semester when we were doing calculations in that? And this is one reason why we like to write units out and things like that. If I look at these delta H values and the specific heat values, I was given those on the problem. It probably means I'm going to need them at some point, right, for the calculations. Well, let's look at the units on that. For delta H, kilojoules per mole. The specific heat's joules per gram Kelvin. So what it tells me is to use those guys up on top, those delta H values, I'm going to need to have something in moles to cancel out those mole units, right? Because energy is usually in joules or kilojoules or something like that. I wasn't given any information about moles. I was only given a weight, that 42 grams. The other thing is I look at those specific heats, and those have a Kelvin factor in them. So it tells me temperature is going to be involved somehow. And I have a temperature change here. And so I'm going to need to know something with temperature just from a units perspective to cancel out. So that's why I went ahead and generated my delta T value and my molecular weight, because I'm thinking I'm probably going to need those at some point in it. So that first energy transition that I have, that's going from 35 to 78 degrees. So I use my specific heat value, and I have 42 grams times my specific heat value, okay, which is right here. That's for the liquid, okay, this is the specific heat for the liquid. And I'm in the liquid phase. And then here's my temperature change. So now Kelvin cancels Kelvin, grams cancels grams. I'm left with the unit of joules. And if I do the math, I would get 4.17 times 10 to the third joules. I'm expressing it in kilojoules just because that's a more normal one. And remember, 1,000 joules equals 1 kilojoule. So now, what I calculated here is the energy required to heat the liquid from 35 degrees to 78 degrees. So once again, thinking back to this, I had to heat that liquid up. The liquid wasn't a solid, it was already a liquid. I had to heat it up to get it up to that boiling point. So there's energy involved there. That's what the calculation I just did there. But I'm not finished yet because I want to vaporize it, right? So I've gotten up there, and now I said there's energy involved in taking that liquid and then turning it into gas. So we're at 78 degrees. We want to vaporize it. So we use delta H DAP vaporization. So delta H vaporization to vaporize. We see what that constant is. Okay, we go back up here and look. Delta H vaporization was the 38.56 kilojoules per mole value. So now here, at 42 grams, here grams canceled on the first part, 8 canceled out nicely, but here we don't have grams in the denominator, we have moles. So I want to change that 42 grams to moles. So that's why I'm multiplying 42 grams times 1 over 46 grams. Remember, this 46 gram value came from our molecular weight that we calculated. So now we change this into moles. The moles unit here cancels with the moles in the denominator of this delta H value. And now I get a kilojoule value if I go ahead and do that math. So the total energy for this transition that we talked about had 2 steps to it. Okay, one was getting from the temperature we were at up to the temperature we wanted to be for the boiling, and then the vaporization. So we take the value that we got in the first step is 4.17, and add it to the second step, and that's what we're doing down here for total energy. 4.17 plus 35.2 gives us 39.4 kilojoules. Any questions about this one? Yes.
Underneath in part A, underneath the specific heat for the liquid,
Mhm.
the, what is that? Is it 8-K?
Yeah, sorry about the handwriting. It's G grams dash K. So it doesn't mean grams minus K. It just means grams and K, but you usually just write it with a dash. So what that means is in the numerator, you have joules as a unit, and in the denominator, you have grams and you have Kelvin. Okay, so that's where here, when you do this calculation, the 42 times that number, the grams here would cancel the grams here. It would be joules per Kelvin. And then when we multiply this by the Kelvin, the K's cancel and we're left with just joules as a unit. So one of the problems with looking at my homework is you have to suffer my handwriting. So, but the good thing about this, if you look in the book, and the other thing I would say is I do post these questions along with the homework answers in case you don't have your book with you. So I know it's kind of a pain to lug that thing around. The questions are typed up nicely by the book, so you can actually read their stuff. So, okay, any other questions about this? And we're going to do another one here. Okay, this has a little bit more in terms of steps. In this one, we want to know how much heat is required to convert this same amount of ethanol. So we're still working with ethanol, same amount. So with all those constants that we used, not constants, but those delta H values and specific heat values and that we were given still hold for this. We'll be using those same values. How much heat is required to convert that ethanol starting at minus 155 degrees C to the vapor phase at 78 degrees C. So now we're starting out lower, starting in a freezing area. So the first thing we need to do is we need to heat the liquid to 114 degrees, okay? So if we go ahead, no good place to put that thing. So we're saying we want to go from minus 155 to 114 C. So this minus 114 C. So that delta T is 41. So the difference between 114 and 155 is 41. So we've got our delta T here. We've got our grams of ethanol. And then we go ahead and do our math. We cancel our K and G units out, and we're left with joules. Once again, I'm expressing it in kilojoules. And we get 1.7 kilojoules. So what we've done is we've gotten to the temperature to get from a solid to a liquid form. And now we need to melt the solid. And that's this next calculation. So we're going to use that specific heat. We have 42 grams. We need to change it to moles again because our value is 5.02 kilojoules per mole. We do that conversion using that molecular weight that we calculated previously, and we get an energy value for that second step. Well, we still have a couple more steps to go. So now we've converted it over, so we've gone from solid up to the temperature to melt, then we melted it, now we're at liquid, now we've got to heat that liquid up, because now we're at minus 114, now we've got to heat the liquid up to get it to 78 degrees, okay? So now we do that using our delta H value here. We have a temperature change of 192, that's the difference between minus 114 and 78. And we do that calculation and we get 19 kilojoules. So now we are all in a liquid state, and now we need we've taken it up to that vaporization temperature, and now we need to actually vaporize the liquid. Once again, then we use the appropriate factor there, which is 38.56 kilojoules per mole, and get a value of 35 kilojoules. What you do then is, that again, you add up those 4 steps, and that's what we're doing on the bottom here. You add up those 4 steps to get 60 kilojoules, which is the total for that transition from start to finish. So the first one we looked at, we had a couple of steps. This one was a little more involved because we had 4 steps, but the idea is kind of the same. Think of it as you're raising something up to a temperature, that's a step. If you get to the temperature where that activity is going to occur, whether it's melting or boiling or whatever, then you have to calculate that heat. And so it all goes back to that heat diagram that we talked about. You know, if you understand that and just kind of the logic behind those steps, then the calculations are just more a factor of picking out the right delta H, picking out the right specific heat. Usually, I shouldn't say usually, it always tells you which delta H it is, which specific heat it is, what it is for. And then it's setting it up, if you think of your units and keeping them so that your dimensional analysis is working out so that you're winding up with kilojoules or joules at the end, then you should be okay. A lot of opportunity to mess up with your calculator. So I'll say it again, like I did last semester, make sure you're comfortable using your calculator, okay? Any questions on this stuff? Okay. Just for fun, I'm going to put up the heating curve one last time before we move on. Spend some time getting comfortable with that and understanding the changes. Okay. So the next thing we're going to talk about is vapor pressure. So no matter what the temperature, if you have a liquid, some of those molecules are going to get enough energy to where they escape the liquid. So in other words, the liquid, remember, has those intermolecular forces, which are kind of keeping things together, keeping things in the solution. Well, you're going to have some of those that have enough energy so that the intermolecular forces don't hold them anymore and they will vaporize. The higher the temperature, the more of them do that, as you might imagine. But you always have some. And so what we have here is on this plot is the blue plot kind of shows you a distribution of those molecules at a lower temperature, and then the red one is at a higher temperature. The dotted line that we see kind of coming down, that's, in this case, we're defining that as the minimum kinetic energy needed for those molecules to escape. And this is just showing that as you increase that temperature, you see a little bit of shift of all those molecules in terms of where they're at, and you see you get more that can suddenly now escape the solution. So kind of makes sense. You put some energy in, you disrupt some of those intermolecular forces, more stuff can escape. When we talk about vapor pressure, what we're talking about is really that equilibrium between molecules in solution and molecules in the vapor phase. And so one way of kind of studying that is this example down on the bottom. So we have, in this case, it's ethanol, some liquid ethanol above. We have a container below that's been evacuated. So in other words, they've sucked all the air out, so there's no pressure. And then you open up the ethanol and put some into that container below, then close it back up. What's going to happen is the molecules, in this case the ethanol, some of it's going to stay in solution and some of it is going to go into the gas phase. And at some point, it'll reach what we call equilibrium. And that just means that the amount that's in the solution and the amount that's in the vapor phase don't change. We get exchange back and forth where some of the vapor go up, but if some of them go from liquid to vapor, then some of the vapor will go down. And that equilibrium is, when you measure that, that's telling you what the vapor pressure is. As you'll see here in a moment, vapor pressure of a liquid is the pressure exerted by its vapor when the liquid and vapor are in dynamic equilibrium. And dynamic equilibrium means that exchange going back and forth, back and forth. The individual molecules change, but the totals don't, okay? We say that liquids that evaporate easily are volatile. And volatile liquids have a high vapor pressure. So that makes sense. If it's a material that, in that situation we just looked at, has a lot of molecules in the gas phase and the vapor phase, then that's going to exert a bunch of pressure. That's going to increase the pressure. And so liquids that are volatile have high vapor pressure. What do we mean by volatile also? So when I think of volatile liquids, one that always comes to mind for me is acetone. So a lot of times you use acetone in the lab. Acetone is in some of the fingernail polish removers. But if you've ever been around acetone, if you spill it, unless it's a huge amount, but if you just spill a kind of small amount, by the time you go get a paper towel or rag or something to clean it up, it's gone. It's evaporated. That's very volatile, very high vapor pressure. You spill some water, it might sit there for a day or two if you don't clean it up, right? Much lower vapor pressure. So volatility directly related to vapor pressure, and all of this has to do with those interactions, those intermolecular forces within the material. If it's really strong, it's not going to have a high vapor pressure. It's going to want to stay together. If it's not as strong, then it goes up and you have it more in the gas phase. If you smell something, it's most likely got a high vapor pressure, right? That means it's volatilized. Now, some things are stinkier than others, but fundamentally, you know, if you spill something and you don't have to clean it up, high vapor pressure, because it's volatilized pretty quickly. When we talk about boiling point is related to vapor pressure in that boiling point is defined for a liquid is defined as the temperature at which the vapor pressure equals atmospheric pressure. Normally, we consider atmospheric pressure to be 760 torr or 1 atmosphere. And that when we think of it in that respect, we call it the normal boiling point. Because boiling point is related to atmospheric pressure, that's why if you go up like in the mountains or something, the boiling point decreases with altitude because atmospheric pressure decreases with altitude. So that's why if you live like, you know, I guess in the mountains in Colorado or something high up, stuff's going to boil at a lower temperature. And that's why, because of the atmospheric pressure is different in those higher altitudes. Okay, so this leads us to something called supercritical fluids. So if you recall, we've said over and over and over, there's 3 types of matter: gas, solid, and liquid. Well, as you kind of go on, you kind of learn that isn't exactly correct. There are some others, and one of those is supercritical fluids. And what a supercritical fluid is a state where, okay, so first of all, let's just talk about how if you have a gas, you can liquefy it when you apply pressure. If you put enough pressure, you can liquefy it. There comes a temperature point in which a gas cannot be compressed anymore. That's called the critical temperature. And then also the pressure needed to compress liquid at a critical temperature is called its critical pressure. And then finally, as you get beyond these points, that's where you get to something called a supercritical fluid. So it's not a gas, it's not a liquid, it's kind of in between those phases. And these are some materials that we have the critical temperature and critical pressure for. The one I want to mention is carbon dioxide, this one here, CO2. So CO2 is used, well, it's used to do extractions a lot of times. And one reason is because carbon dioxide is a pretty safe chemical. We think CO2 is not real dangerous. And one thing that it's used in is if you've ever drank decaffeinated tea or decaffeinated coffee, there's a good chance that they decaffeinated it by doing a supercritical fluid CO2 extraction. There's other ways to do it too, but those usually involve chemical solvents, and then you got to get rid of the solvents. And so the CO2, you just change the pressure and the temp settings, and it just goes away. So CO2 is often used for decaffeinating coffee or tea. Okay, so something that is associated with understanding phase changes and understanding supercritical fluids in that is something called a phase diagram. And we'll look at that in a moment, but first let's just talk about it for a moment. The phase diagram shows the states of matter and what they are with different temperature and pressure combinations. It also shows the triple point and the critical point. The critical point is the temperature and pressure. If you go beyond that, then no longer do you have liquid and gas phases, you have that supercritical fluid phase. And the triple point is where solid, liquid, and gas are in equilibrium with each other. So in other words, you got all three kind of going at the same time. So let's take a look at the phase diagram. If you ever take physical chemistry, you'll get to talk a lot more about these. Physical chemists love these phase diagrams. But this is a generic one. This isn't meant to represent any particular compound, but they all have the same presentation. They have on the x-axis, they have temperature. On the y-axis, they have pressure. And then what you're getting here is you're seeing a particular temperature and pressure combination is the material in the gas phase, solid phase, liquid phase, or if you get crazy enough, is it supercritical fluid? So on here we see the T, and in the lower left-hand corner, that's the triple point. Remember we said the triple point is where gas, liquid, and solid are in equilibrium. C is that critical point where if we go beyond that in terms of temperature and pressure, we then have a supercritical fluid. And then the arrows back and forth show along, like in this green line here, we see possibility of a interface of solid and gas. This red one with the arrows, we have an interface between liquid and gas. The blue up here, we see an interface between solid and liquid. So that's kind of the general idea of this. So if I told you that the pressure was at about this P and the temperature was at about the T, I could come and go over here for pressure and then up here for T. So the people on Zoom can't see what I'm doing, but the people in the class are enjoying it very much. Another reason to come to class in person. And so where you would wind up is kind of at the end of this arrow and then under vaporization. So what that tells me is under that pressure temperature combination, I would have a liquid, okay? And that's what these are used for, is to know what state of matter you're dealing with. And you'd say, well, why do I care about that? Well, we'll get to that in a little bit here. Here's the phase diagram for water. So we actually have some numbers. So we see here, we see the triple point of water is 0.00098 degrees C and 0.00603 atmospheres. Not very common in terms of pressure. I mean, 0 degrees C, that's not a big deal, but that's really no pressure at all. The critical point for water, 374 C in 217 atmospheres. So you really got to put a lot of heat and pressure into it to get water to form a supercritical fluid. The next one is the one I want to show you. This is carbon dioxide. Remember I said this is the one that is used to do extractions of coffee or tea to remove the caffeine. And so what I want to point out here is the critical point is 31C, 73 atmosphere. Not too bad. 31C, gosh, that's like room temperature, right? Usually people consider 25 to 30C that range room temperature. So temperature is pretty reasonable. 73 atmospheres, well, we said atmospheric pressure, we consider that to be essentially 1. So 73 is higher than that, but 73 atmospheres isn't a crazy high pressure. So you can kind of see why, from an engineering perspective, it's probably pretty not too difficult to get to this area up here, because now I just got to go above 31.1, and I got to get above 73 atmospheres, and that puts me in this supercritical fluid part. So to create supercritical CO2 isn't really that crazy or that difficult to do. That combined with the fact that it's not a hazardous chemical, CO2 is pretty safe, tells you one reason why it's a real popular supercritical fluid solvent to do not only that tea and coffee extraction, but there's other extractions they do with that as well. So. Okay, the next thing we want to talk about a little bit is liquid crystals. So does anyone have a liquid crystal with them right now? I bet you do. So liquid crystals are what, like I have like a cheaper watch that display, most likely liquid crystal. A lot of the computer screens and TV screens have liquid crystals in them. So what liquid crystals are is a substance that doesn't go directly from solid to liquid. And so that intermediate state is called a liquid crystal. And what makes it, and it tends to be like here we have some pictures. Here's the liquid phase, here's the liquid. They tend to have this kind of milky look to them. And what's going on there is that the molecules in there have order to them. And you'll see some pictures in a few moments which explain that a little bit better, make it a little clearer. But liquid crystals, and so in this example, liquid crystals were first discovered when some people were working with cholesterol years ago, that cholesterol apparently has some liquid crystal type properties. So liquid crystals are often composed of rod-shaped molecules that are somewhat rigid. So think of like looking like a cigar. And then in liquid phase, the orientation is random, okay? As they get into that liquid crystal phase, you start to get some order in terms of the physical arrangement of the molecules. And these are the definitions of these different orders. So in pneumatic liquid crystals, molecules are ordered in only one dimension, and that's along the axis. Okay, the axis is like the length of that cigar. Symmetric A and C liquid crystals are ordered in 2 dimensions. So they're ordered along the long axis, and they're also ordered in layers. Cholesteric liquid crystals, pneumatic-like crystals, are layered at angles to each other. And so in other words, you have one layer to the next, and the orientation of the molecules by a fixed angle. And so these are kind of stacked, so they're like double order, and you get like this spiral pattern. It's easier to look at these pictures and then talk about it. So starting from left to right, we go from liquid to cholesteric. Liquid, you see the cigar-shaped molecules, it's all kind of random. Some are up, some are down, some are sideways, all that. As you start to get in the liquid crystalline phase, here first we have the pneumatic. What we see is there's still a little bit of randomness, but they're all pointing upwards, right? They're all pointing in the same direction. So no longer do we have like this one down here on the liquid that's kind of sideways. They're all up. Now with Smectic A, we keep that vertical alignment there. They're all in the same direction. And now we've got two layers of it. Okay, we've got a layer here and a layer below, top and bottom. Smectic C, what we have there is we have vertical alignment, so long axis alignment, and then we have layers, except now they're kind of tilted a little bit. You see how they're all tilted the same way. It's not a randomness, it's order. And then finally, in the cholesteric, we got a lot going on. We've got different layers, okay? And within those layers, we've got a certain amount of order to each of those. And so what you can do is, if you have these arrangements like this, you can do things to these. You know, you can have electrical impulses go through and other things go through, heat, stuff like that, and it causes them to move together. And that's kind of how the liquid crystal thing, in a real simple way, works. So these crystalline structures that come about are what you get in that milky phase. And not all compounds do this. There's a handful of them that do, but that's where the liquid crystal stuff comes from. Okay. I want to just do one thing before I let you go, is looking at this phase diagram. I'm not going to go through it right now, but what I would expect you to be able to do with this is if I give you a temperature and pressure, okay, so this is in Kelvin. So if I said 60 degrees Kelvin and 10 to the third atmospheres, you would be able to tell me what phase the material is in, okay? So go through this, kind of look at this a little bit and see if you can do that, but that would be the expectation on this type of a question, all right? Any questions on what we went through today? All right, that's it for today, and we'll see you next week. Thank you.